Hi, and welcome to Chapter 4. Environmental and occupational epidemiology use the same tools as epidemiology generally, but there are a few important distinctions. In environmental or non-occupational settings, exposure levels are often low and homogeneous among large groups of people. For example, most of us have some level of BPA and chemicals from non-stick pans in our bodies. Consequently, large sample sizes are often necessary to detect exposure-disease relationships. Environmental epidemiology studies are almost always observational, since it's almost always unethical to randomize people to environmental exposure groups. In occupational settings, there may be high exposure levels compared with the general population. This can make detecting an exposure-disease relationship more feasible, but there are usually smaller numbers of people to study, which can limit the sample size. The workplace is essentially a natural experiment, more conducive to epidemiological studies than the general population. However, studies can be impeded by politics and business interests. Although still a concern, occupational exposures of interest are not limited to chemical agents. Hazards may include stress, shift work, and ergonomics. There are a few key words in this epidemiology definition. The first is distribution. Who has the disease? Which age groups, sex, socioeconomic status? Where are cases of disease, geographically speaking? When did the cases of disease occur? These questions answer person, place, and time, and make up what is known as descriptive epidemiology. There's more on that in a future slide. The next important word is determinants. Smoking is a determinant for lung cancer. Sun exposure, and specifically sunburns, are determinants of melanoma. These are often referred to as risk of causal factors. Epidemiology is the primary science used to assess health and disease in humans. Studying the relationship between exposures and disease is, of course, important for disease prevention. Using the lung cancer and melanoma examples just mentioned, this is why smoking quit lines and sunscreen exist. We are attempting to reduce exposure to cigarette smoke and UV radiation, respectively. Epidemiology can also assess whether an exposure is protective. For example, exercising outdoors, the exposure, is associated with increased adherence to exercise routines compared with exercising indoors. Eating vitamin C, the exposure, prevents scurvy. Austin Bradford Hill established a set of criteria that can be used to help determine if an association between exposure and disease is causal. This article is in your required reading. All criteria should be taken into consideration simultaneously. However, exposure must always precede the disease. This isn't always easy to determine, especially if cross-sectional study designs are used. More on that later. For example, if you asked someone if they had asthma, yes or no, and measured air pollution outside of their home on the same day, you wouldn't necessarily know that the air pollution caused the asthma. Other criteria include consistency. Do multiple studies show the same thing? Large effect size. How much added risk is attributable to the exposure? Dose-response relationship. More exposure causes more disease. And biological plausibility. It makes sense from a biological standpoint. There are several kinds of epidemiologic studies. Descriptive studies do exactly that. They describe the disease in regards to person, place, and time. This is the distribution part of the epidemiology definition provided on the last slide. Descriptive studies do not formally test any hypotheses. They do not ask if exposure A is associated with disease B, but they may suggest areas for further investigation. For example, descriptive studies may suggest a relationship between a particular disease and occupation. If so, epidemiologists would follow up with an analytic study to help determine if there is an association. Descriptive studies are often used in public health practice, typically by governmental organizations to determine burden of disease. Ecological studies, sometimes called correlational studies, examine exposure-disease relationships at a population level. For example, a cancer epidemiologist might note that there is a higher rate of leukemia in the south of the city near a hazardous waste site. Does this mean the hazardous waste site is causing the leukemia? You really can't say because you don't know if those with the risk factor are the same people as those with the disease. You need to do additional studies that assess this relationship at the individual level. The higher rate of leukemia could be due to a number of other factors, including population demographics or other exposures. Ecological studies are most useful for hypothesis generation. They're usually fairly cheap and easy to do and suggest areas for further inquiry with more expensive analytic studies. The exception to this general rule is time series studies, in which change in one variable, like air pollution levels, is compared to change in another variable, like emergency room visits for cardiopulmonary disease, over time, usually measured daily. Last, etiological or analytic studies test a specific exposure disease hypothesis among individuals. They are divided into experimental and observational. Experimental includes the randomized clinical trial. These are frequently used in clinical medicine to determine if one treatment outperforms another. They are rarely used in environmental epidemiology because it's unethical to randomize people to environmental hazards. The exception to this is randomizing people for intervention trials, in which a proposed method of reducing an exposure or a protective factor is assessed. Observational studies are, by far, most frequently used in environmental epidemiology. These natural experiments are subject to confounding, and all observational study designs have inherent limitations. Cohort studies are useful when separate exposed and unexposed groups can be assembled. They may be used in occupational studies when there is a group of people exposed to an occupational hazard. They may also be used to assess the effects of unique environmental exposures, such as those that occur following an environmental disaster. Some studies follow large cohorts of people over time to assess a variety of exposure-disease relationships. These are prospective studies in which the groups are assembled and followed forward in time. They are expensive and take longer to conduct because epidemiologists must wait for disease events to occur, but they provide more accurate information on exposure, especially when clinical or environmental samples are required, and disease, especially when disease events are difficult to remember. Alternatively, cohort studies can be done retrospectively. That is, the epidemiologist establishes cohorts of people with a past exposure and assesses current health status. These types of studies are less expensive and don't take as long to conduct, but some pieces of information may be missing, like exact exposure levels. Cohort studies are best for when the exposure is rare, but the disease is common. Establishing cohorts based on exposure allows the epidemiologist to concentrate the number of exposed persons in their study. In contrast, case control studies are good for when diseases are rare but exposures are common. Epidemiologists select cases with disease and controls without disease for inclusion into the study. They look back in time to assess prior exposure. Remember Hill's criteria that exposure must occur before the disease. Exposures are compared between these two groups to determine if a particular exposure is more common in those with disease than those without. This results in an odds ratio, which compares the odds of exposure in the diseased group compared to the odds of exposure in a control group. If the case control study is well designed, it should give the same answer as if it was conducted as a cohort study. However, it can be difficult to design a case control study very well. Controls may not be representative of the general population, and it may be difficult to determine past exposures with certainty, and cases may remember past exposures differently than controls. For these reasons, bias is often problematic in case control studies. Cross-sectional studies are also sometimes called prevalence studies. In these studies, exposure and disease are measured at the same time. Since temporality can usually not be inferred, this is considered a weaker study design than cohort and case control studies. However, cross-sectional studies are often the only possible study design for surveys, including large national surveys with many observations. These studies often suggest that further research using stronger and more expensive study design is warranted. Bias is the distortion of the true relationship between exposure and disease. This can make the point estimate exaggerated or underestimated. In other words, it can create false association or mask a true association. There are many sources of bias, but the most common are listed here. Selection bias is when the relationship between exposure and disease is not the same in the study population as it is in the general population. In other words, the study population is not representative of the general population. A low response rate can result in selection bias because those who participate in the study may be different than those who do not. For example, maybe they are more motivated to participate because they have more severe disease. The healthy worker effect represents another type of selection bias, since workers are typically healthier than the general population. Unlike some other types of bias, you cannot control for selection bias. Confounding results when a third variable related to the exposure and disease distorts the association. For example, you might be interested in the relationship between lead exposure and reading level. You would consider socioeconomic factors like income and maternal education as confounding variables because lead exposure and reading level can both be influenced by socioeconomic factors. You can correct for confounding variables in the analysis, but only if you have information on the confounding variable. Therefore, it's important to consider potential confounders when you're designing your study so that the data can be collected. Information bias occurs when information about either the exposure or disease is incorrect. When exposure is measured differently between disease and non-disease subjects, then bias can force your point estimate to go in either direction, exaggerating or underestimating the association. This is a concern in case control studies, as disease people may have more accurate information on their exposures than non-disease, even if it's just because they've considered their exposures more in light of their disease. The concepts on this slide get into nitty-gritty of epidemiology, so if you've already taken it, it's a review. If not, consider it a preview. You might have to refer to the text as it takes a couple readings for these concepts to sink in. The point to remember from the first two bullets is that the type of analysis depends on the kinds of variables you have. So if you have dichotomous variables, one of two conditions is true, the person is exposed or not, then you would calculate rate ratios, risk ratios, or odds ratios, depending on your study design. When one or more of your variables are continuous, for example, blood pressure and exposure levels, you would use a regression analysis. Epidemiologists and biostatisticians are concerned with precision, the sharpness of the point estimate. The confidence interval tells you how precise the point estimate is. Tight confidence intervals reflect a narrow range of plausible values and means greater precision. Precision is related to statistical power and significance. The greater the sample size you have, the greater the statistical power and the tighter your confidence intervals will be. Confidence intervals that do not overlap with 1 indicate statistical significance. Another important concept is validity. Internal validity reflects whether the results of the study are true and if the investigators arrived at the right conclusion. Once a number of studies have been conducted to assess the relationship between exposure and disease, a meta-analysis can be done to summarize the existing evidence. This complex analysis is a weighted average of the results from the existing published studies. It can combine the results of different study designs, for example, case control studies and cohort studies, into a common measure of effect. Meta-analyses are published as separate studies. Sometimes these exposure response analyses can complement the toxicology analysis to help set permissible exposure levels for the public or in the workplace. In environmental public health and practice, it's common to receive concerns about disease clusters from the public and from workers. A cluster is an elevated number of cases of disease in a defined area over a defined time period, suggesting a common exposure or cause of the disease. These may be cases of cancer in a particular neighborhood. However, most times clusters are difficult to confirm. This may be because it's difficult to establish geographic and temporal boundaries. For example, you may get very different epidemiological estimates depending on how far back you go in time to look for cases. A common reason for perceived clusters not actually being clusters is that people may think of cancer as one disease, but in reality there are many different types of cancer with very different risk factors. Clusters are usually fairly small, limiting the statistical significance of any epidemiological study that is done. Also, you may not have information on the background rate of disease to determine if your observed number of cases is greater than what you expect. Cluster investigations are usually case control studies in which exposures are assessed retrospectively. Exposure levels or even the types of exposures may not be known. Cluster investigations usually don't yield an epidemiological association between exposure and disease. Occupational clusters are usually less difficult to investigate because the workplace is a defined boundary and exposure. Modern environmental health practice is increasingly including not just environmental hazards such as lead or radon, but also settings such as the built environment and even climate change. In these cases, the exposures are multiple, sometimes even mixed in their ability to harm or protect health, and are also more complex to measure. Environmental and occupational epidemiology is also different depending on where you live. In developed countries, occupational epidemiology has expanded beyond exposure to chemical, biological, radiological, and physical hazards to include factors like stress and shift work. In many developing countries, people are still exposed to high levels of classic occupational and environmental toxicants like lead, cadmium, and arsenic. Surveillance and control are a higher priority than epidemiological studies, which have largely already been conducted for many of the existing hazards. Thank you, everybody.